All right, I'll record this. I'm not going to work off my slides. I'm going to write them. I'm going to write what I'm saying here. So if you want to take some notes, it should also be recorded. I want to imagine for a minute that we all work at Alcoa, the Aluminum Company of America. The Aluminum Company of America. It's headquartered in Pittsburgh. That's where I was born. This doesn't all have to revolve around me, but just a few personal comments now and then. My brother used to work for Alcoa, not in Pittsburgh, in Brazil. He moved down to Brazil, and then he got a job with Alcoa. The company's headquartered where we were born. So he worked for that. So what Aluminum Company of America? They make aluminum. All right, that's what they like to make, aluminum. You don't dig aluminum out of the ground. You do not find this in the ground. Although I pointed out that this, I may have pointed it out before, this stuff doesn't rust or corrode like iron. It eventually will. You throw that in the ground, in a landfill, and it'll eventually disappear, and it will become aluminum oxide. And actually, this is called bauxite. In geology, they'd say bauxite. This is what's actually mined out of the ground. And actually, I told you my brother moved to Brazil. That wasn't really that unusual for him to work for Alcoa, because although it's headquartered in Pittsburgh, Brazil has a lot of bauxite, and Brazil has a lot of hydroelectric plants, hydroelectric dams, and they generate electricity with water power from dams. Why is that good? This takes a lot of energy to make aluminum from bauxite. It takes a lot of energy. So if you can get the energy cheaply, you can make the aluminum more economically. So Brazil is probably Alcoa's primary production site for aluminum. Mining the bauxite, making the aluminum, and then making stuff out of the aluminum. One way to do this is to react it with carbon. And you get aluminum, and you get carbon dioxide. So there's a chemical reaction. It's kind of wordy, don't you think? There's a lot of words there. So this is the reaction. This is not necessarily the reaction Alcoa uses, but it is a possible reaction. I think they industrially use a little more complicated reaction, but one that is more efficient and uses less energy and all that sort of thing. So, all right, so first of all, a chemical reaction takes these are the reactants. They're on the left side of the equation. And then you go to products on the right side of the equation. This is what you're starting with. Sometimes you'll hear me refer to them as the starting materials, the raw materials, the reactants. And these are what you are reacting together to produce this product over here. These products, whatever the products are. So chemists distill this down into a little neat shorthand thing. And when we're all done talking about this little reaction here, hopefully you will start appreciating how much information is packed into a little chemical equation. There's a lot of information packed there. First of all, you have to write the chemical formulas of the reactants and the products. All right? So aluminum oxide, it's made up of aluminum and oxygen. And what is the correct chemical formula for aluminum oxide? K2O3. Okay, and you're getting that because this is a +3, right? This is a -2. And so we cross that, and we get Al2O3. as the correct formula of aluminum oxide. Carbon is being reacted with aluminum oxide as elemental carbon. It's not a compound, it's an element. And so when there is an element, you usually just pull that symbol right off of the periodic table. I say usually. If it were oxygen, you would write it as oxygen, the way it exists as an element, and it exists as molecules of oxygen, okay? So if it were oxygen or nitrogen or hydrogen or any of those diatomic molecules right there, you would write them as their diatomic molecule. But everything else, if it's carbon or cobalt or iron or potassium as an element, you just write the symbol there. So carbon. Products. Oh, we're producing an element. This is elemental aluminum right here. That's what Alcoa is. So all we need is the symbol for aluminum. Carbon dioxide. What's the formula for carbon dioxide? CO2. Okay? So we've gotten this far. We've got the correct chemical formula for the reactants and then what is produced by this reaction, the products. And we're not going to change those. Eventually we're going to start talking about balancing this chemical equation. But one thing we're not going to do when we try to balance these equations is change those formulas. We can't just willy-nilly say, oh, I'm going to write that as a CO. Because what is CO? Carbon monoxide. And that's not what this reaction is producing. So if you change the formula, you're actually changing the whole nature, fundamental nature of the reaction. Okay, so you can't change these formulas once you have identified what the products actually are. And you need to write the correct chemical formulas for these reactions. Okay, now one other thing you're going to see, I'm going to put these down, explain them, and then I'm going to erase them for right now. One other thing you might see here are these little parentheses after here, and in this particular case, they would be this. It'd be an S, 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 G. And what those things are telling you, they're telling you just one simple thing. What is the physical state of this material at room temperature? Not necessarily at the temperature of the reaction, but here at room temperature. Because actually, when Alcoa makes this aluminum, it comes out as a liquid. It's melted. Have you ever seen, well, you've seen the iron, you've probably seen pictures of them making iron, and they're pouring the iron out of a big cauldron, and it's red hot, and it's liquid iron. And they pour it, and it flows, and then it cools, and they squeeze it down into sheets or I-beams or whatever they want to make out of it before or as it's cooling. They're making that. So we don't put here as a liquid, that's what's coming out of this reaction. It's coming out as a liquid, but then it cools down to room temperature, and it is a solid at room temperature. Okay? So the symbols you will see is an S, which means it's a solid. You'll see a G. Carbon dioxide is a gas at room temperature. You might see, after water, you might see an L, which is telling you it's a liquid. You might see this, NaCl, solid. So that's like the salt in your salt shaker. But you might see an equation like this, and the AQ means that sodium chloride is dissolved in water. It's an aqueous solution. So those are some of the symbols. SG, L, AQ. I'm trying to think what else. There are a couple other subscripts you might see there. I always get to this point and I forget what other ones, because these are the ones you see most popularly.
See, that's like the only ones we saw in our 1105 in our books.
Those are the only ones?
Yeah, those are the only ones.
Yeah. Yeah. So I'm going to erase that now. Just I want you to be aware, and I guess I'll leave them there, but I usually erase them at this point because I want the focus to be on balancing this equation, and I don't want anything extraneous to that right now. So, but just be aware of what that is. That's not going to affect the balancing of the equation. It's telling you the physical state it's in. Okay, so now let's balance the equation. Balancing the equation means you got to have the same number of aluminums on both sides of the equation. Same number of aluminums, carbons, and oxygens on both sides of the equation. And all I got down here is just kind of my worksheet. This isn't really the final answer. The final answer is just this balanced chemical equation. And there's a little bit of an art with some experience. You will start seeing what to do. You have to start somewhere. And as I look at this, I'm going to just stand back here and kind of get the 30,000 foot view of that. I stand back and look at my equation. I do have 2 aluminums over here and only 1 here. I have 3 oxygens and 2 oxygens. I have 1 carbon and 1 carbon. So right at the outset, just the way we've written the formulas, the carbon is balanced, but aluminum and oxygen aren't. Carbon is going to be easy to balance at the end, the last step. Why? Because it sits over here all by itself. And I've already said once, you can't balance this by just changing formulas of things. You have to balance it now by changing coefficients in front of these things. Coefficients. And the best place to start on this one actually is the oxygen. There's 3 here and 2 here, and I can't just put a well, I got to get a number of oxygens that could agree on both sides of the equation. And what number of oxygens would that be? 6. If I take this times this, that's 6 oxygens. So to get 6 oxygens over here, what do I need to put in front of this? A 2. A coefficient now, and this is what trips up a lot of students, that coefficient doesn't just apply to the aluminum. It applies to the entire compound. With that 2 right there is really saying I've got 2 of these. I have 2 Al2O3s. And since there's 3 oxygens in each one, that's 6 oxygens. So how do I get 6 oxygens over here? Put a 3 right here. All right, so that 2 right there gives me 4 aluminums and gives me 6 oxygens. That 3 over there gives me 3 carbons and 6 oxygens. So I've got the oxygens nailed down. All right, carbon and aluminum are really kind of neat because they sit there all by themselves. So I can very easily get 4 aluminums by just putting a 4 in front of the aluminum. And I can very easily get 3 carbons by putting a 3 in front of the carbon. And now as I look down through it, whenever I kind of log what elements are over here, I log them over here in the same order, so that I can inspect very easily. That's balanced. I got the same number of everything on both sides of the equation. That's a balanced chemical equation. All right, so now let's look at what we have here. What is it telling us? What these coefficients now could be read to say is that 2 moles of aluminum oxide are reacting with 3 moles of carbon. And it's going to produce 4 moles of aluminum and 3 moles of carbon dioxide. It could be read at the molecular level. You could say 2 molecules of this plus 3 of those atoms are going to produce 4 of those atoms, and 3 molecules of carbon dioxide. That's at the atomic level. Alcoa isn't real particularly interested in just how many atoms they're making. They want to get this into the real world, the macroscopic world, and so we start talking about moles. All right. Remember, this is 12.01 grams per mole. So really, it's saying it's going to take 36.03 grams. What is that? 3 times 12.01. Well, to get your dimensional analysis, 3 moles. Oh, let's do it the way I've been saying I usually do it. 3 moles times 12.01 grams per mole equals 36.03 grams of carbon. I picked on that one because it was real easy to get the molar mass of that right off the periodic table. To get this molar mass, I've got to add those together. 2 aluminums, 3 oxygens. We would get the molar mass. So you could get molar masses for each one of these things up here and multiply them by that, and you know how many grams that would be. All right, so talking about it in moles brings it into the realm in which we can weigh it in the lab. Alcoa is actually interested in tons, metric tons of this stuff, or tons of it, large quantities. But what this says, if I look at these numbers now, I can use them in a way. Really, it says that 2 moles. There's going to 2 moles of for every 2 moles of aluminum oxide that react, you get 4 moles of aluminum. For every 2 moles, let's put it over here, 2 moles of aluminum oxide I'm going to react, I'm going to need 3 moles of carbon. That's the ratio in this chemical reaction. If this is the amount of aluminum oxide I want to react, I'm going to need 3 moles of carbon. If I only have 2 moles of carbon, it isn't all going to react. It requires a minimum. It requires that amount of carbon to react with that amount of aluminum. So you can use these coefficients to relate any 2 things in this reaction. So the Environmental Protection Agency comes to Alcoa and says, how much CO2 are you producing? Well, they know that for the Environmental Protection Agency knows for every 2 moles of aluminum oxide Alcoa is reacting, they're going to produce 3 moles of carbon dioxide. That is the emissions that are going to come out of their plant. It's the amount of global warming gas they're going to produce. How much CO2. And so companies like Alcoa, they're working on how to capture that CO2. They're talking about carbon capture. That's what they're talking about. Capturing that CO2 somehow so it doesn't go into the atmosphere, and therefore lower their CO2 footprint. For every 4 moles of aluminum that are produced, 3 moles of CO2 are also produced. All right, so you could use these coefficients to relate any 2 items in the equation. Okay, so that is your chemical equation. What a chemical equation is, how to relate to what you're seeing there. If I give you a chemical reaction, say, hey, here's a chemical reaction. This is what's happening here. This is what's being produced. And it says balance it. Well, then balance it, assuming those are the reactants, those are the products, and those are the formulas of them. Let me see if I can find those slides in here where we're balancing chemical equations. We'll get back to these molar calculations. Well, there's a mole day. So there's our balloons back there. If they were filled with oxygen, they'd be about that size. What that is, that's getting as close to about 22.4 liters as we can. And you'll relate to that in chapter 5 when we get to gases. But 22.4 liters of a gas at standard temperature and pressure would be a mole of gas. And those are filled with helium. So there's a mole of water, 18.02 grams of water, 63.55 grams of copper, 63.55, right off the periodic table. So that weight of copper is 6.02. These are all 6.02 times 10 to the 23rd, whether it be atoms or formula units. Calcium carbonate, 100.09 grams of calcium carbonate would be a mole. 32 grams of oxygen would be a mole. This is going to be 6.02 times 10 to the 23rd water molecules. Just get familiar with this. A mole is that number. All right, let me get to balancing some equations, and then I'm going to give you a worksheet. Features of the chemical reaction. Here's another example right in the slides. Here's the decomposition of mercuric oxide to form mercury and oxygen. So you're decomposing it. I left this out on the aluminum. I could have put that in there. That's usually either a flame or electrical energy. It's some form of energy that's needed to cause this reaction. They're showing this reaction right here. Mercuric oxide, kind of a reddish powder. You heat it really hot in a hood because you're going to be driving mercury vapors out of there. Yeah, you got liquid mercury here, but now you've raised the vapor pressure of that mercury, so you're driving mercury out, and the oxygen gas is escaping. So all you have left behind is liquid mercury by heating mercuric oxide real hot. Okay, now just keep in mind you started right here. Mercuric oxide is producing mercury, and you can see now elemental oxygen. But I don't just write an O, because O doesn't exist in just oxygen atoms will automatically combine together to form O2 molecules. So that is the way we see it. And so you can see right away I've got 2 oxygens over here, so I gotta have 2 HGOs. That balances my oxygens. But now I gotta come back and look at it. My mercury is not balanced, right? So that drives me to put a 2 in front of the mercury. Okay, I just want to show you how they got to that balanced equation up there. They started with these formulas. And then they said, okay, how do we balance that equation? 2 HGOs yields 2 HGs plus O2. So 2 moles of mercuric oxide is going to produce 2 moles of mercury and 1 mole of oxygen, elemental oxygen. Well, let's see if they said anything else here that I didn't say. So, products. This is a little confusing. Products, reactant, must be specified using, so the reactants are written on the left of the arrow, products written on the right of the arrow. Physical states are shown in parentheses. So there you go. Mercury is a liquid at room temperature. There are only 2 elements that are liquids at room temperature. That's why these are blue on this periodic table, because they exist as liquids at room temperature. The red ones exist as gases at room temperature, and the black ones, and even these here, these are going to all be solids at room temperature. I know they are because they're, well, I say I know they are because they're so big and heavy and bulky, but so is this atom right here. This is a bit of a conundrum. That's a neat word. Use that sometime. Conundrum.
It's a word of the day.
It's a word of the day with moles. All right, conundrum. That is a liquid. It's just a heavy, bulky atom, and yet it's a liquid. You would think it would be so heavy and bulky that it would form a solid. But those are some of the anomalies of science. I have a few slides here. I just wanted to do an example or two. Okay, all right, let's do a couple. Balance the following equations, and then I'm going to give you this and have you work on it for about 5 or 10 minutes. I want you to plow through some of these. Let's just do a couple different examples. Here's silver nitrate reacting with ferric chloride to form ferric nitrate and silver chloride. This would actually be a double replacement. A double replacement type reaction. The silver is going to come into the chloride. The iron is going to switch with the silver. If you looked at your solubility table, well, let's not go there. That'll complicate things right now. So let's just look. We got silver, we got nitrogen, we have oxygen, we have iron, not fluorine, iron, oh, and chloride. Got a lot of stuff in there. Silver. Now, that's true. We got nitrogen and oxygen right here. But let me tell you, when I'm doing one like this, if this helps you, fine. If it doesn't, forget it. I see that I got NO3 here, and it remains intact. Okay, so that is a nitrate, right? That's a nitrate ion. and it stays nitrate. It's nitrate on one side of the equation, it's nitrate on the other. There's only one of them here, and there are three of them over here. So what I do is I just simplify my list a little bit. Since it remains as a package deal, I keep it as a package. It won't always do that, but in this reaction it is doing that. You follow me? All right, so what do I have? I have one of these, one of these, one of these, and three of those. And on this side of the equation, I have one of these. What happened? On this side of the equation, I have one of these. I have three of these, one of these, and one of these. Right? So sometimes you have to kind of look at this, and you got to start somewhere. You got to start somewhere. I got three of these and only one over there. I got one of these and only three over there. So where do you want to start? You want to balance the chloride or the nitrate?
Do the nitrate.
Do the nitrate. Okay, so we've got three nitrates coming out here. FeNO3 parentheses 3 means there's three of these over here. So how do I get three of them over here? Put a 3 in front of there. And that balances your nitrates. So what did that do to the silver?
You have 3.
Now we got 3 silvers. So how do I balance my silver? Put a 3 in front of the silver. Oh, I'm sorry. This thing is too touchy. Put a 3 in front of there. Now, Mark, maybe you may be able to help me figure out how to mute my screen here a little bit.
Oh, because I have the...
Yeah, don't you have a...
I have the Surface Go.
Surface
I don't
Go.
know about the Surface Pro. It's too advanced for me. I can't do it where like I move the screen.
Well, I don't know why they call it the Pro, because it's doing things I don't want it to do. Now look, we put a 3 in front of the silver. We put a 3 there to balance that 3, and look at what it did. It gave us 3 chlorides along with it. Are you following me? Okay, what some of you are following me. You're saying that, but I want to make sure everybody recognizes that when you put a 3 here, we are talking about 3 of those things, okay? Just because the 3 is right in front of the silver doesn't mean it just applies to the silver. It applies to the whole compound. And I know that I know where you're getting that thinking, because when we put a 3 down here, I've told you that a subscript here refers only to the element before it. So this 3 only applies to that chloride, doesn't apply to that iron. But if I put a 3 here, it applies to the whole package after it. Just always keep that in mind. I don't know how many times I have seen students look at that, 3H2O, and tell me there are 6 hydrogens there and there's 1 oxygen.
Wrong.
That's wrong. There are 6 hydrogens there, and how many oxygens? 3 oxygens. You with me? That's how I've seen it over and over again, interpreted incorrectly. They apply the 3 to the hydrogen, and they forget that there's this oxygen back there, and there are 3 of them there. So don't forget that. And we got a balanced equation. Okay, go ahead and balance that one. Here you got nitrogen reacting with hydrogen to form ammonia. That is it in words. got 2 nitrogens. So how many do you have here?
I'm gonna need 2 over here.
So
I have
how do you
one.
get 2?
1. I have
You
1
only
over
have
here.
1. So how are you going to make it 2?
I'm gonna put 2 in front of it.
Okay.
Two
All right.
in.
All right. So how many hydrogens does that give you?
It'll give me 6.
Okay.
So I'm gonna have to make this one then. Put a 3 in front of it. to make
There
it
you go.
6.
Okay. Okay. You got it? Where is it? Yeah. Everybody got it? Okay, so if you keyed in on the nitrogen right away, because there's 2 there, there's 1 there, I'm going to make that 2. And that gives me 2 nitrogens, but now I got 6 hydrogens. So to get 6 hydrogens, I need to put a 3 right there. Okay. Let me blow this one up right here. I shouldn't say blow up because we are going to blow things up today out there. We're going to start blowing some things up. Okay, now I want to do one, and there's one below here that I'll have you do. This is combustion. And I'm going to put a adjective in front of it, complete combustion. And what do I mean by that? Is it produces CO2. Complete combustion. You can burn these things, whether it be gasoline or this is propane, by the way. So we are now talking barbecue. All right? This is a white tank. This is the gas. It's in the white tank out there by your barbecue. Propane gas reacts with oxygen, forms CO2 and water. You can incompletely burn these things and you produce carbon monoxide. That's another reaction. So if you starve it for oxygen or you don't give it enough oxygen, it won't burn completely. Same way in your car. Your car generally should have CO2 coming out of the back, CO2 and water. But if the carburation, the fuel injectors aren't working properly, you're not getting enough air, your gasoline won't burn completely. And you'll get some carbon monoxide. All right, so this is propane. Now I'm going to give you the choo-choo method. I taught this for a while, and one of my students said, oh, that's the choo-choo method. And I'm writing it carbon, hydrogen, oxygen. I want you to balance these equations in that order. Carbon, hydrogen, and oxygen. So watch me. I'm going to give you an example of that right now. I'm starting over here, and I can see C3H8. So I got 3 carbons, and I have 8 hydrogens, and O2, I have 2 oxygens. That's where I'm starting. So I'm not going to write down any numbers over here. I'm just going to come over here and say, all right, I'm going to start with my carbon. I've got 3 carbons. The only thing over here that has carbon in it is CO2. So I can put a 3 right there and get 3 carbons. This is what I mean by starting with carbon. Okay, now I'm going to move down here to the hydrogen. I got 8 hydrogens. The only thing that has hydrogen over here is H2O. All of this hydrogen in the reactant is coming out as water. So how many waters do I need to give me 8 hydrogens? 4. So I put a 4 right here. 4 times 2 is 8. And there, my carbon and my hydrogen are balanced. Okay, now, when you're at this point and you know how much CO2 and how much water is being produced, you ask yourself, how much oxygen is represented in the products? 3 times 2 is 6. That's where I'm getting this. And 4 times 1, there's a 1 there. 4 times 1 is 4. That's a total of 10 oxygens in my products. Follow me? So how many O2s have to react? 5. 5 of these. 5 times 2. And it's balanced. Okay? That's the choo-choo method. That's Mr. Eoch's choo-choo method. And I need to give my student a byline because they called it that. All right? Now, let's skip over this one for a second. Do this one. Now, we're going to do the complete combustion. This is pentane. This would be one of the ingredients in your gasoline, in your gas tank. You would have pentane, hexane, octane, all these. And it's going to be complete combustion, which rips it down to carbon dioxide and water. And you go ahead and balance that. Okay, what's the coefficients in front of the carbon dioxide? And the coefficient in front of the water? And so 5 times 2 is 10. 6 times 1 is 6. So what's the coefficient for the O2? 8 times 2. All right? Okay. Now, we're going to do one more that's a little bit harder. It's the last one. C8. Work on that one. C8H18. Use the choo-choo method. You're going to run into a problem. Work with pencil, because you might not get this right the first time. This one's a little bit, do the choo-choo method, but there is something more we have to think about on that one. The bottom one. Oh, sorry. There we go. Okay. Okay, let's take a look at this one. You run into a little bit of a problem, didn't you? What the British would call a sticky wicket. Okay, so here's the CHO. Let's see what that sticky wicket is. You got 8 here, so you put an 8 there. You've got 18 hydrogens, so what did you put in front of the water? 9, at least initially you did. And then what did that give you? Well, 8 times 2 is 16 oxygens, and 9 times 1 is 9 oxygens. It gave you an odd number of oxygens, right? That's the problem. You got an odd number of oxygens. That is 12 and a half oxygen molecules. 12 and a half would balance it. Would be balanced. But what chemists don't like in these kinds of balanced equations are fractions.
Same. 12.5.
Or 12.5, same difference. 0.5.
No electric.
12 and a half or 12.5 oxygens. But we want to get that decimal or that fraction out of there. So we want to get that out of there. What can we do about that? Well, if you multiply 12 and a half by 2, you get a whole number. Because, I mean, what you're doing is you're multiplying that half by 2 and you're getting a 1. You're converting it into a whole number. So 2 times 12 is 24. 2 times a half is 1. So you get, 2 times 12 and a half is 25. You get to a whole number. That's beautiful. Okay, however, if you are going to double the amount of oxygen that it's going to be involved in the reaction, you got to double everything else. You got to double the amount of this, this, and this.
Gotcha.
All right? If you're making pancakes, and you have a cup of flour and a cup of milk and a tablespoon of oil and what else? And 1 egg. I don't know what the recipe is. All right, but let's say that's the recipe, and that makes 6 pancakes. But you want 12 pancakes. You've got to use 2 cups of flour, 2 cups of milk, 2 tablespoons of oil, and 2 eggs, don't you? You have to double everything in the recipe. You can't just say I'm going to use 2 eggs and get 12 pancakes out of it. So right here, you can't just double the oxygen and say that's good. I got rid of that fraction. So 2 times 1 is 2. 2 times 12 and a half is 25. 2 times 8 is 16. And 2 times 9 is 18. All right, you got to double everything. I gave that once on a quiz or an exam. A student said afterwards they got it wrong, and they said, "I got that, but I thought those numbers were too high. Never saw an equation with a 25 as a coefficient." But yeah, that is what balances that equation. All right? So let's just make one. This is the only concept we're going to cover today